Okay, in this video I want to talk about even and odd functions a little bit. So a function is defined to be even if f of minus x is the same as f of x. And so you're thinking that's kind of like the function f of x is equal to x squared, where it's symmetric left to right. A function f of x is odd if f of minus x is minus f of x. And so an example of that would be f of x is equal to x cubed. And that's another kind of symmetry that's symmetry around the origin. So 180-degree rotation symmetry. Reasons that we care about these, if we happen to integrate an even function from, say, -2 to +2, then essentially we're going to get the same area either way, and so we can just find the area on the right side and double it. Same thing here for an odd function. If I was integrating from -2 to 2, we would have the same area on the right as we would have on the left, but with opposite signs, and so the integral of an odd function should spit out a 0 when we're going from negative number to positive same number. Okay, reason this is important is when we start to look at Fourier series. So if we started with an even function, then our formula for the Fourier series is this, with formulas for a0, an, and bn. Only since we have an even function, this first one is an integral of an even function from -p to p, which is a symmetric region, and so this is actually just going to be the same as double the right hand side. So I'm going to double that and make it 2 over p integral from -p to p, 2 over p, just the right hand side, 0 to p, f of x dx. Okay, and this is because we're integrating an even function, and from -p to p we're going to get the same area as doubling the right hand side. If I look at this next one, we have an f of x times a cosine. Cosine is also an even function, and it turns out an even function times an even function will still be even. So just as a quick example of that, here's an even function times an even function. The answer is also an even function. So it helps to think about it in terms of polynomials, because even is going to correspond to even exponents. So an even function times an even function, this whole thing would be even. And the integral of an even function from -p to p would be doubling the right hand side. So integral from 0 to p, we're going to double it, make it 2 over p, and then keep the same inside. And the third one, if I have an even function times an odd function, an even function times an odd function would be, in this case, x to the 5th, which is an odd function. So inside the integral here we have an odd function, and the integral of an odd function from -p to p should be spitting out 0. So bonus, if we started off with an even function, we can make 2 of our integrals a little bit simpler. We just have to integrate them on 0 to p instead of -p to p. That usually ends up working out a little bit nicer because it's easier to integrate plugging in zeros. And then this is the one that's really convenient. We don't even have to do this integral since it just spits out a 0. Okay, let's look at the same thing if we had started with a function f that was odd. Then our a0 would be 1 over p, integral from -p to p of f of x dx. This is now an odd function. Integral of an odd function from -p to p would just spit out a 0. A sub n would be 1 over p, integral from -p to p, f of x times cosine n pi x over p. Again, this is an odd function times an even function. Odd times even should be odd, and an integral of an odd function would spit out a 0. And lastly, bn, 1 over p, integral from -p to p, f of x cosine n pi x over p dx is going to be an odd function. Oops. No one saw that. I'm certainly not recording this. If we have an odd function times an odd function, an odd function times an odd function would be, in this case, 3 plus 5 would be 8. We should end up with an even function. So if this is an integral of final result is an even function, then this should be back to our original case where it's symmetric, so we're just going to get double the right-hand side. Okay, so let's talk about why this matters, what this can tell us. It means that if we started with an even function, our Fourier series is going to have an a0, an an, and the bn is going to be 0. So that means essentially our Fourier series is just going to look like this if we started with an even function, since bn is going to be 0. On the other hand, if we started with an odd function, then the a0 is going to be 0, the an is going to be 0, and we're going to end up with just this part of the sum. So f of x is equal to sum of bn sine n pi x over p. So what that means is that if we know ahead of time that our function has one of these kinds of symmetries, it's an even function or an odd function, then it's going to be a lot simpler to calculate the Fourier series. Also, notice the connection. Even functions, we're only seeing even pieces. The cosines and the constants are showing up. Those are actually even functions, so it makes sense that they would show up in your series expansion of an even function. If the function is odd, it would make sense that you'd only get sines. If your function is neither even nor odd, then you would expect to have both kinds of pieces, both sines and cosines, or both constants and sines and cosines.